Hi everyone, it's Mr. Kwan here. Today we're going to be talking about linear programming. Now, linear programming is a technique that can be used to solve problems that have limitations on the variables called constraints. If the constraints can be expressed as linear inequalities and the function that is trying to be maximized or minimized, called the objective function, is a linear function, then the problem is called a linear programming problem. Linear programming is widely used by businesses for problems that may involve many variables, sometimes more than 100. When you graph all the constraints, they form a system of linear inequalities. The solution region that the graph creates is called the feasible region. Let's look at an example. That was a lot of terms that I just threw at you. Example 1 says, Mr. Kwan needs to find a side hustle because teaching basically pays him with coupons and sadness. Wah wah. Mr. Kwan decides to open a little food stand where he will sell chicken burritos and feta wraps for the vegetarians. Mr. Kwan always sells everything that he brings. Okay, so let's talk about some more constraints. Since Mr. Kwan must teach class and respond to 9 million emails, he only has 240 minutes to prepare food. Each burrito takes 10 minutes to make, and each wrap takes 5 minutes to make. He also has limited space for keeping the food until they get sold. The burritos are 2 inches in height, and the wraps are half an inch high. Mr. Kwan's total space will hold up to 40 inches of height. Part A says find a combination of burritos and number of wraps that Mr. Kwan can make that will satisfy all of the constraints above. Now, you're probably saying to yourself, I think there's a pretty easy combination or easier than other combinations that we can find that will satisfy these constraints. And if you're like me, you're always trying to look for the easiest answer and the least complicated. And so my first thought went to, well, even without doing a whole bunch of math, I think I can see that if I were to make one burrito and one wrap, that should meet the constraints that I am given. So let's just go ahead and make sure that that is in fact true. Let's talk about the time constraint. So if I made one burrito, that would be 10 minutes. And then if I made one wrap, that would be 5 minutes. And if I added those together, the total amount of time that I would be using is 15 minutes, and that is in fact less than or equal to 240. So I've met the time constraint. What about the space constraint that I have? Well, let's see. So one burrito is 2 inches high and one wrap is half an inch high. And so if I added those two numbers together, then I would have 2.5 inches, and that would be definitely less than the 40 inches that I have as kind of a maximum. So I've gone ahead and I've answered the question. It says find a combination of burritos and number of wraps that I can make and sell that will satisfy these constraints. So one burrito and one wrap. However, that's not really going to make me the most amount of money. And, you know, let's be honest, that's all anyone really cares about is the money. So maybe we could think about one more combination. Let's try and see if we could do 3 burritos and maybe 5 wraps. Let's see if that will work. So time. So each burrito takes 10 minutes. So I would be multiplying 10 times 3 since I'm making 3 burritos. And each wrap takes 5 minutes. So I would multiply 5 times 5. And that would be 30 plus 25, which is equal to 55. And again, that is definitely less than or equal to 240. So that is okay. I meet my time constraint. Am I going to meet my space constraint? Well, we know that each burrito is 2 inches in height, and we have 3 of them, so I would multiply 3 times 2, plus I know that each wrap is half an inch in height, and there are 5 of them, so the resulting expression that we would want to simplify is 3 times 2 plus 5 times 1/2. So that is equal to 6 plus 2.5, which is equal to 8.5. And that again is definitely less than or equal to 40. So both of our constraints are met, and so this is also an acceptable solution. However, we're going to see in the next part of our example 1, in part B, that we want to try and maximize profit, and we're going to use that, or we're going to do that by using linear programming. All right, part B says, suppose that Mr. Kwan plans on selling burritos for $4 each and wraps for $3 each. Graph the feasible region to help Mr. Kwan decide how many of each type of food he should sell to maximize his profits. The very first thing that you want to do with these types of problems is to define your variables. Every time I teach this topic, I always say this, and people still don't listen to me. Define your variables. It's very important in these types of problems. So the thing that we are ultimately trying to figure out is how many burritos should I sell and how many wraps should I sell so that I can make the most amount of money. So I'm going to create 2 variables. One of them I'm going to call B, and I'm going to let that be the number of burritos I sell. Mr. Kwan sells. And I'm going to let W equal the number of wraps Mr. Kwan sells. So ultimately that is our goal. We are trying to figure out a value for B and a value for W that will maximize our profits. The next thing that you want to do is you want to figure out what is called your objective function. And that is the thing that you are trying to either maximize or minimize. And in this case, we are trying to maximize profits. And our profits, let's say we're not taking into consideration costs. And so let's say I'm just profiting whatever money I make off of selling these, because normally profits is revenue minus costs. But let's just say our profits is whatever money I make from selling these. So I would make $4 for every burrito I sold, plus an additional $3 for every wrap I sold. So I then have now created the equation P equals 4B plus 3W. That is the thing that we are trying to maximize. Okay, and then the next thing that you want to do is you want to figure out your constraints. Remember, constraints are inequalities. Okay, so remember earlier we had a time constraint and we had a space constraint. So our time constraint, we know that each burrito takes 10 minutes and each wrap takes 5 minutes. What that means is that we basically have 10B, 10 minutes for each burrito, plus 5 minutes for each wrap. If we add that all together, kind of like we saw in part A, all of that has to be less than or equal to 240 minutes. So that's our time constraint. Our space constraint was that for each burrito that we sold, those would take up 2 inches, and then add that with each wrap that we sold, that would take up half an inch, and we needed that to be less than or equal to 40. Okay, so based off reading the problems, it seems like we would be done creating our constraints. However, there are actually 2 more constraints that we need to think about. I would like you to pause the video for a moment, go back and read the problem, and see if you cannot figure out what should my other two constraints be? Okay, so hopefully looking at the graph or grid that we have available for us might have given you a hint. And in the context of this problem, it wouldn't make sense for us to say that we want to sell a negative amount of burritos or a negative amount of wraps. That's why we're only looking at the first quadrant in the grid that we're given. So another way of saying that is that the number of burritos we make has to be greater than or equal to 0, and the number of wraps that we make also has to be greater than or equal to 0. So if we were to graph both of those inequalities, basically that is limiting us to being in the first quadrant. Now let me label my axes, and you can swap them however you want, but I'm going to go ahead and let the horizontal axis be my number of burritos and my vertical axis be the number of wraps. And we need to go ahead and graph our feasible region by graphing all of our constraints and then shading in the feasible region. So I'm going to go ahead and scale my tick marks on my grid. I've gone ahead and just filled out some of the tick mark values. Basically, each tick mark represents 5 units. And now what we want to do is we want to graph our inequalities. So I'm going to use, let's see, blue to graph my first inequality. Since W is our vertical axis, I'm going to go ahead and solve my inequality for W. So I have 10b plus 5w is less than or equal to 240. If I subtract 10b from both sides, I would have 5w is less than or equal to negative 10b plus 240. And then I would divide everything by 5, and we would get w is less than or equal to negative 2b plus 48. So let me now plot that here. So that would be about here. And instead of going down 2 over 1, I could scale that to go down 20. So that would land me at, let's see, 40. So that would be 28, and then I could go over 10. So that would be like right there. So I could, from 38, I could go down another 20. That would, let's see, land me at 18 and then go over another 10. So that would be about right there. Did I mess that up? (28 minus 20). I did mess that up, sorry. So 28 minus 20 should be 8, not 18. So that would be about here if I went over 10. So I'm going to go ahead and connect those now. So it's going to look something like that. And now I'm going to graph my second inequality in red. So again, I'm going to solve that for W. So I have 2b plus 1/2 W is less than or equal to 40. I'm going to subtract 2b on both sides. If I do that, I would get 1/2 W is less than or equal to negative 2b plus 40. I just swapped those terms so that it's kind of in the y equals mxb form. And now I would divide both sides by 1/2, but that is the same thing as multiplying by 2. So I'm going to multiply the left-hand side by 2, and then I'm going to also multiply the right-hand side by 2. And if I do that, I get W is less than or equal to negative 4b plus, let's see, 40 times 2 is 80. and we want to graph that now. So our intercept is 0, 80, and then our slope is -4/1, but we could scale that, and we could have it go down 40 and over 10, and we could have it go down 40 and another 10, so that would be like right there. I'm going to use my ruler this time. My handy dandy ruler. Okay. Awesome. So now I want to think about my feasible region. And notice that I didn't graph these two. However, I guess we should go ahead and do that. So I'm going to graph b is greater than or equal to 0 in this violet color. So that would be here, and we would shade up. And then w is greater than or equal to 0. I'll graph that in green. So that's going to be our vertical axis, and then we are shading to the right side of it. Okay, now I'm going to let you figure out for the red and blue line where we're shading for those. So I would suggest that you pause the video and figure out where you're going to shade for that, because in a second, I'm going to highlight the feasible region. Okay, so hopefully you figured out that the feasible region is this where I'm highlighting the yellow right now. Okay, so I'm going to use black to label this. This is our feasible region. Now, I am going to use, let's see, what color do I want? I am going to use black to highlight a couple of points. So there's this point here, this point here, this point here, and this point here. Notice that these 4 points basically cover our feasible region. Let me draw it down here. Basically, it's forming this kind of shape. Here, and what I've done is I've basically highlighted these 4 points here on our graph. Now, these points here, they are called, sometimes you'll hear them called vertices. That's the plural version of vertex. So singular would be vertex, or you might also hear them called corners of our feasible region. Now, it turns out that these points are quite important, and we need to do some work with those. And that will occur in our next video.